This video lesson is on graphs in 3D. If I go too fast in this video, please keep in mind that you can always pause the video and you can replay it as many times as you like. So we'd like to be able to graph points or any other surfaces in 3 dimensions, especially because we live in a 3-dimensional world. In order to describe 3 dimensions, we need to be able to move forward and backwards, left and right, and up and down. So unlike graphing in 2 dimensions, where we only needed the x and y axes to fully describe any point, in 3 dimensions we're going to need 3 axes. So we have the x, y, and z axes. I've labeled the letter that corresponds to each axis next to the positive direction for that axis. So you'll notice that x is positive when it's moving forward. You can think of that arrow as moving forward out of the screen or back into the screen. Y is going to be positive if we move to the right and negative if we move to the left. And z is going to be positive if we move up and negative if we move down. Notice that when we had 2 axes, it split the space into 4 quadrants. Now that we have 3 axes, it splits the space into 8 regions that we call octants. A point in 3 space can be uniquely described by its 3 coordinates: how far we've had to move along the x-axis, then how far we've had to move along the y-axis, and finally, how far we've had to move along the z-axis. So let me illustrate this with an example. So let's say that we wanted to move 1 unit along the x-axis, 5 units along the y-axis, and down 2 units along the z-axis. We would like to find what point lies at the meeting of all 3 of these measurements, and it sometimes helps to illustrate this by drawing dotted lines that indicate how far we're going in each direction. It's even more helpful sometimes to fully complete the box. So you can kind of imagine that there's this rectangular box, and the point that we're interested in is the point that's found by moving 1 unit along the x-axis and then traveling along that orange dotted line for 5 units along parallel to the y-axis, and then moving along that turquoise line down 2 units. So this gives us the point P, and we can describe the coordinates of this point as 1, 5, -2. The coordinate box is the name for this object that I just drew, and really its main use is just helping us see where the point is, because notice if I didn't draw it, it would be very hard to figure out if the point P was lying above the z equals 0 mark or below the z equals 0 mark, or even whether the point P was using a positive or negative y value. Alright, so on page 2 of your packet, you should have a drawing that looks similar to this. And you'll notice that in order to get to the point P, I've had to move 3 units along the positive x direction. I've moved 4 units to the left, which means -4 in the y direction, and up 2 units in the z direction. So the point P is given by 3, -4, 2. There's one more example on this page, and the one on my slides is slightly different than the one you have on your packet. So notice that the one on the slide here seems to have us moving backwards 1 unit in the x direction. I think on your packet it has us moving backwards 2 units in the x direction. On my slide I have it moving backwards 4 directions in the y direction and up 1 unit in the z direction. So the coordinates for this point on my graph, yours will be slightly different, is -1 for the x-coordinate, -4 for the y-coordinate, and +1 for the z-coordinate. All right, so next we'd like to talk about graphing multiple points. So this is at the bottom of page, 2 on your packet. So we'd like to be able to just try graphing these 3 points. The first point that I gave you was 0, 5, 7. So that means that we're going to go over 0 in the x direction, 5 in the positive y direction, and 7 in the positive z direction. And when I draw my dotted lines, notice that my box is actually an infinitely skinny box. It really is just a flat plane, sort of like a piece of paper, that has no thickness along the y-axis. And so the point can be found by just connecting the dots along the y and z axes to get the point P. We can do a similar process for the point 4, 0, -1. So notice this time that we've moved 0 units in the y direction. And so once again, if we draw our little box there, it has no thickness along the y-axis. So it really is just a plane again. And the point Q is as indicated. Finally, for the point R, this one's going to be a little bit more challenging. The coordinates are 1, -1, 2. And we can draw the coordinate box, just as we've done before, and find the point R. So we'd also like to be able to describe flat surfaces, which we're going to call planes. And although we're going to get to this in more detail in a few days, we already have a little bit of the tools that we need to be able to talk about surfaces. There's 3 different types of coordinate planes. Each of these coordinate planes completely ignores one of the 3 axes and looks at all of the points that lie in just the other 2 dimensions. So the first is the xy plane, and this is actually the plane that we're used to graphing on. For the xy plane, we're going to assume that z is 0, and we're going to look at the surface that's formed by just spanning x and y. So we get a flat surface. This surface is supposed to only pass through z equals 0, and it takes on every x and y value. Notice that I've had to draw it as kind of a parallelogram. This plane really does extend on forever, though. So any point where x and y have any values that they want, but z is 0, any point of that form will lie on the xy plane. The yz plane, similarly, is one where x is equal to 0, and the y and z values are allowed to be anything that they want. Once again, I've drawn this as a finite rectangle, but really this is a plane that extends all the way up and down in the z directions and all the way to the right and left in the y directions. And finally, the xz plane. This is the plane where y is set to be 0, and this plane is going to extend all the way forward and all the way back along the x-axis, and all the way up and all the way down along the z-axis, but y is always 0. Drawing planes is very difficult, so just do your best to communicate the important information or the main ideas, and don't worry too much if it doesn't look like a perfect masterpiece. At this point, you can pause the video and try problem 3 on your packet. Alright, next we'd like to talk about finding the distance between 2 points in 3 dimensions. Recall that in 2 dimensions we could take 2 points, P, given by x1, y1, and Q, given by x2, y2, And we found that the distance from P to Q was the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And visually what was happening here, if we have the 2 points in the xy plane, we can connect them with a straight line, and we want to know what the length of that line is. So we can break this up into a right triangle, and then we only have to consider the horizontal distance that we've traveled and the vertical distance that we've traveled. So the horizontal distance is x2 minus x1, the vertical distance is y2 minus y1, and the distance that we want is the length of this hypotenuse. So using the Pythagorean theorem, we can get this distance formula that I gave you above. At this point, you can pause the video to try to complete problems 4 through 9 on the packet. Just a warning, these problems are kind of hard, but I'm hoping that you have the skills that you need in order to answer them. Just do the best you can, and we'll go over them in class next time. The last slide that I have for you is a refresher on completing the square. So remember, if we have something of the form x squared plus bx equals c, where x is a variable and b and c are both constants, we'd like to write the left-hand side as a perfect square. So that's our goal for completing the square. In order to do that, we're going to add 1/2 of b and then square that. We're going to add that value to both sides of the equation. So for example, here I have x squared plus bx, and then I'm going to add b over 2 quantity squared to both sides. So that gives me x squared plus x squared plus bx plus b over 2 quantity squared equals c plus b over 2 quantity squared. Notice that that makes the left-hand side a perfect square, namely x plus b over 2 quantity squared, and the right-hand side we can just leave alone. So let's try an example. Let's say that we have x squared plus 3x plus y squared plus 6y equals 0. This is the equation of a circle, and we'll be able to get it into the standard form of the equation of a circle by completing the square. This is useful because it'll help us find the center of the circle as well as the radius of the circle. So in order to do this, we're going to first split off the x values and the y values. I'm going to first complete the square with the x values, which I've underlined in orange. Notice that half of 3 is 1.5, and 1.5 squared is 2.25. So that means that in order to complete the square for the x's, I'm going to have to add 2.25 to both sides of the equation. In order to complete the square for the y values, the green underlined part, I have to take half of 6, which is 3, and square it, so that gives me 9. So that means that I'm going to add 2.25 and 9 to both the left and the right side of the equation. This is to make sure that the equation really is still equal on both sides. Alright, so the nice thing about completing the square is once we've done this process, both the x terms and the y terms are going to split up into nice perfect squares. The x terms are going to give me x plus 1.5 quantity squared, and the y terms are going to give me y plus 3 quantity squared. And then on the right hand side I just added the 2.25 plus 9. So this tells me that I have a circle of radius the square root of 11.25, and the center of this circle is at negative 1.5, comma negative 3. This should be kind of a familiar concept to you, and in the packet I'm asking you to extend this to three-dimensional circles, which we also know as spheres. Alright, so the last problem on the packet, try number 10 and see if you can complete the square to find the standard form of the equation of the sphere, and then give me its center and its radius. Good luck.